Hi everyone, today we'll be presenting a login bypass challenge we built as part of our Securebank application. We'll cover what the vulnerability is, followed by a breakdown of the tech stack we used to build the application. From there, we'll go through how we exploited it, show a quick demo, and then explain how it could have been prevented. So first, we'll give you a bit of a background on the exploit, which is built around a double encoded SQL injection combined with an access control flow. This challenge targets the flaw in how the application decodes input and assigns user roles, which, when combined, can be used to bypass the login system entirely. The application attempts to block SQL injection by filtering out certain keywords, but that filtering is limited. It doesn't account for values that are encoded once or even multiple times. This opens the door for attackers to send in a payload that appears harmless at first, but is later decoded into input that bypasses validation. When a user logs in, the server assigns a session cookie with a role field, either user or admin. That field controls access to key parts of the app. If you can trick the system into thinking you're an admin, you bypass all normal restrictions. Our objective was to manipulate the login input in a way that bypassed both client-side and server-side filters, ultimately gaining admin access through SQL injection attack and exposing a critical flaw in how the application handled authentication and input validation.
Hey everyone, my name is Sunny. So I'm just going to give a quick overview on what this challenge is. Essentially, a CTF capture the flag challenge, which is focused on SQL injection vulnerabilities in a simulated banking application. So players are meant to exploit flawed authentication, transaction manipulation, and data retrieval to gain unauthorized access, escalate privileges, and corrupt financial records. So given that, for our tech stack, we chose Next.js 15 for client server-side rendering and React 18 with TypeScript built in. So essentially, this lets us build a fully interactive front end with a typed backend using built-in API routes using React's app router. And the entire app runs on top of SQLite 3. And we use this to create the schema to build on raw SQL, not object relational mapping. So what this does is this gives us full control over how queries are constructed and how input is passed. We think this was a crucial implementation for demonstrating SQL injection vulnerabilities realistically, especially in components where things such as a transaction search bar and feedback's response field was left perfectly wide open without sanitation. So we did implement partial sanitation on sensitive routes like login and registration, but left other endpoints exposed to show how even a seemingly normal search box could compromise the entire DB. All user inputs hits a real database, and none of the data is mocked or static. Essentially, you're querying live data with real role accounts and user linked transactions. We also used cookie-based session management with the cookie signature no dependency, and we use salt factoring to essentially parse the password into the DB. What this does is it signs the session tokens using a secret from the environment variables, and every page you visit cross-references the signature to ensure that the session data hasn't been tampered with. So even if hypothetically someone bypasses login through SQL injection, they still need to forge a valid signed cookie to elevate the privileges, which ties directly back into the whole security theme we have going on. The front end is styled with Tailwind CSS using inline styling, and the UI is built with perfectly beautifully typed TSX components. This leaves it consistent, responsive, and fast to iterate. We use toast alerts for the user feedback and Vanta.js to animate a globe background on a landing page, getting a polished feel right from the first load. So overall, we chose a stack not just for the speed, but because it gave us deep control over statically defined data types, data flow considering the amount of tree-linked dependencies used, and user interaction. The UI would be impossible with plain JavaScript and CSS to the depth and vision we saw this project going. So overall, we think this stack makes a perfect overall model for simulating a realistic enterprise-looking and vulnerable banking platform.
All right, so my name is Robert, and I'll be going over the exploitation strategy. So the goal was to log in as the first user in the database, and we just assumed that the first user is the admin user. All right, so here's how we approach the challenge and discover the exploit. After registering a basic user account, we noticed something interesting in the session cookie. It had a field called role, and it was set to user. That hinted to us that there might be other roles in the system, like an admin role, and that the application probably uses role-based access control. Naturally, we tried some classic SQL injection payloads like or 1 equals 1 to test the login, but those didn't work. Both the front end and the back end had filters in place that blocked those kinds of obvious attempts. So to go around the client-side filters, we used Burp Suite to intercept and modify the login request directly. This gave us full control over what was being sent to the backend and let us test different payloads more freely. Eventually, what worked was something interesting, double encoding. Basically, we URL encoded the payload once and then encoded that result again. What this did was trick the server. It would decode the input once before applying any filters, but by the time it reached the SQL query, it had already accepted the malicious content. That's how we got past the filter. Once the payload went through, we were logged in as an admin and got an admin session cookie, confirming the attack was successful.
My name is Daniel, and I developed this attack. So I thought it would be best for me to demonstrate it. So now with that background information from Robert, I will be demonstrating how to do this attack. In order to ensure that the demonstration runs smoothly within the allotted time, I've pre-recorded the walkthrough, which I'll be playing on the next slide. The goal for this attack is to retrieve the first user, which is likely the admin, by inserting a payload into the username, such that we break out of the select statement and have it process select all from usernames where username is equal to XYZ or anything, or 1 equals 1. So the or equal 1 equals 1 part breaks out, and then that will return the very first user while also commenting out the rest of the query. Now we have some client-side filtration where this will not allow us to do it through the front end. So we are going to have to do this using Burp by capturing the requests directly. So our basic payload looks like this. And this will get caught, and we will be told that we're on the right track because it's detecting that we are using illegal characters. So there's filtering also in the backend as well being done. Now, it's good we were told to use SQL comments instead of dashes because they're not encodable. This also gives us a hint that we need to use encoding. So I've gone ahead and single encoded this on URL encoder, and we're gonna put this into the username and try again. Now, when we try this, it still detects it. So now we are gonna try to use double encoding. And this is what that will look like. So double encoding is encoding the payload that I had just shown you before. And when we hit send, it bypasses the filtering and it allows us to get access to the admin account. And as you can see right here, it issues us a session and it issues us a user ID, which is 1. So we know that this is correct and we are now logged in. All right, so that is the demo. The goal for this, hold on, let's go to the next slide.
All right, hey guys, my name is AJ, so we'll be talking about how to prevent this type of attack. There are 4 key defenses, all of which address exactly how our exploit was able to bypass the login system. The first round of defense is using parameterized queries. The root cause of this vulnerability was that application built SQL statements by directly inserting user input into the query string. This allowed our payload, even when encoded, to alter the query logic. Using parameterized queries would have completely prevented this. Parameterization ensures that input is treated strictly as data, not code, which makes SQL injection impossible. The second round of defense is don't rely on filtering. The application attempted to block SQL keywords like select or minus minus through input filtering, but filters are unreliable. Attackers can rewrite their input using encoding or slight variations to get around these blocks. In our case, double URL encoding let us bypass the filters entirely because the server didn't recognize the payload and it's an encoded form. The third round of defense is to decode before validating. The filter logic was applied after decoding the input once, but the server decoded the input a second time before executing the SQL, which turned our safe looking string back into a working payload. Input should be fully decoded before any validation or filtering happens. Otherwise, encoded payloads can sneak through and become active when processed deeper in the backend. The fourth round of defense is to enforce server-side role checks. After the injection succeeded, the app gave us an admin session just based on the query result without rechecking our permissions. Sensitive actions like deleting feedback should always trigger a role check on the server, independent of what's stored in the client session or cookie. Never assume that a logged in user is authorized just because they passed the login page. Now we're going to just wrap this up here. So this challenge showed that filtering user input is not a reliable defense against SQL injection. While the application attempted to block certain keywords, the real issue was that it constructed SQL queries by directly inserting user input. When that happens, even encoded or disguised input can break the logic, as we demonstrated using a double encoded payload. The correct solution is to use parameterized queries, which prevent user input from ever being interpreted as SQL code, regardless of how it's formatted. Finally, it's also important to validate roles securely on the server. In this case, the app accepted our forged login and issued an admin session without rechecking privileges, which made the exploit more damaging. These kinds of oversights are common in real-world applications, which is why understanding how to exploit them and how to defend against them is essential for secure development.